Welcome to the Future of Electricity panel session. My name is Mark Johnson. I'm a program director at ARPA-E. And before we get going, this reminds me of the 9 a.m. thermodynamics class that I teach. Instead of having everyone sitting towards the back, why don't we all move up towards the front, if at all possible? And we'll have a much better dialogue and conversation here. Because what we really want to have is a dialogue and conversation about what are some of the things that ARPA-E has been doing in the whole area of electricity, and also what are we thinking about. And so we've got myself and three of my colleagues here as looking at this area in the future of electricity in this discussion. My name is Mark Johnson. As I said, I've been a program director focusing on electric energy storage as one of the technical areas. Tim Heidel's my colleague, Dr. Tim Heidel. He works on the area of controlling electricity flows. Dr. Sawyer is the assistant program director here as well. She's looking at the carbon capture and utilization aspects of electricity. And then Howard Branz is a program director who's joined us in this past year, as you heard this morning. And he's looking at sort of advanced solar ideas as well. So when you think about the future of electricity, you think about it all the way from generation up through how it's used and transported, and then all the way down to demand. So hopefully we have a little bit of a dialogue on that today. So first question we have is, why do we care about electricity for energy? And this is a Sankey diagram of a typical year, how we wind up using energy across the country. And as you can see, almost between a third and a half of all energy, primary energy, gets used in the form of electricity. Right? So if you're not talking about electricity and looking at the overall system of electricity, you really have a hard time digging into the details of energy. So electricity and energy are integrally connected in this country. Where within the Department of Energy? So on the right you have the eye chart of a typical org structure. Electricity is across the entire Department of Energy, all the way from the early stage basic science areas, looking at advanced computing and basic energy sciences, through ARPA-E, up into the applied offices where you're looking at things like the wind program, the solar program, electric delivery and energy reliability, and then looking in the fossil energy areas and nuclear energy, the generation technologies. We also have a number of focus groups and crosscuts, so things like the Sunshot Initiative, looking at solar, getting it advanced. The Grid Tech Team, where you're looking at groups coming across the department to say, how can we all work together to make sure we're most effectively moving things forward? And then we have a number of intergovernmental partnerships as well. So you're looking at how the use of electricity in the U.S. really is used by the Department of Defense and other agencies as well across the government. After this session this afternoon, there's a session on governmental networking, and a number of those partners are at that session as well. So if you think about electricity as a technology area, this is a typical view where you've got generation, transmission, distribution, you've got industrial, commercial, and residential uses of it. Really, if you go beyond that and think of it as technical topical areas, we can look much more comprehensively, from generation through transmission, distribution, a number of ways where we can seamlessly control the energy, the information about that energy, and also how we wind up using it more effectively and wind up using it more cost effectively. Within ARPA-E, we've got a number of programs that we've already started at this point, where you're looking at things like the carbon capture, use of solar as far as advanced renewables through the Solar Adept program, and a number of individual projects looking at advanced generation through things like our Open FOA programs. In the delivery side, we're looking at things like the Genie program, which Tim will be speaking about, the GRIDS program on energy storage, and the Adept program on power electronics. And on the load side, the uses of energy, things like how we develop technologies to more efficiently use electricity, or things like how we can develop new motors and electric motors, things like that, and make that work better through the REACT program. So, for this panel, why is electricity a priority for ARPA-E? Well, it gets back to our fundamental mission. That is, how do we have greater efficiency, greater economic security, and reduce emissions, and make sure we can have this energy resource as a safe, effective technology for the future, as this becomes an economic foundation and really opportunity moving forward in energy. Where are we thinking next? So we're going to really have these four topical areas. We're going to talk about storage, grid control, carbon capture, and solar. So one thing that we ask you in terms of interacting with the group today is, if you have some questions, please, you can text them, you can tweet them, or submit them directly into ARPA-E. And we have a number of people that are gathering those questions together. So as the panel goes forward, we're going to have about 5 to 10 minutes for each person, but then we're going to have a discussion and a dialogue and some question and answers as far as that. So this is the method for communicating. So I'm going to start. I'm going to talk about electric energy storage. I've been here at ARPA-E just around 3 years at this point. It's been a great time to be here and really looking at that energy storage program that we've wound up standing up. I started by taking a look back and saying, where did we come from? So I found this early technical drawing that came out of ARPA Medieval on how you wind up storing energy, and that is you have water up a hill and you wind up taking it downhill. And so this technology has been the dominant technology literally for thousands of years. So this is a more modern application of that with the Ludington plant in Michigan. And that winds up then being the primary way electric energy is stored in the world. And we can get much better than that because we can store energy in a number of places. We can store it on the generation side. We can store it in transmission distribution and in the load side, both industrial, commercial, and residential side. So how do we develop technologies that can cost effectively do this? A big issue in terms of developing new technology isn't just can we develop some nifty new scientific technique, but can we do it that will get the cost down to the point where it is most cost competitive with hydroelectric. So we really went out and looked for a new technology toolbox, and we also worked with those projects to see how we can wind up developing some first markets to get that technology out there. And our cost metric out there was that we wanted to have it no more than 2.5 cents a kilowatt hour increase in that energy, which per cycle, which at 80% round trip efficiency and 5,000 cycles came back to about $100 a kilowatt hour capital cost. It's a really aggressive economic target that required some really new thinking about the technology. We've also had a number of challenges and needs that are driving this, that overlays on top of this technology. We've got a changing generation fleet and a lot of uncertainty about which direction is the right way to go for the future on that. You've got challenging locational constraints. How do we put in the resources for things like transmission lines through areas into urban populations? And as we saw this last fall, we have robust requirements for reliability and expectations for that. But power really becomes the basis of our economy. So this is a graph that really illustrated one problem on that. That is how you wind up integrating renewables where you have high renewable penetration. Looking at the Pacific Northwest as an example on that. And this is how you match the wind generation, that's the actual generation, with the expected amount. And they've done this historically by balancing the power using hydroelectric, so adjusting things like the Bonneville Power Dam, the output from that. And if you look at the units on that, that's a gigawatt units up and down that they're moving. That's the equivalent of an entire nuclear power plant coming on and off the grid on a fairly quick basis, so 15 to 20 minutes. Now, I've given this exact same slide and used this through the GRIDS program the last couple of years, and I inevitably get asked the question, wow, you just cherry-pick data. So I always take the most recent data, and so this is through about 10 o'clock last night, and as you can see that it's only getting worse. They had about 4.5 gigawatts of wind being generated all day Saturday and Sunday. That came on at the end of the week, and then all of a sudden it just dropped off yesterday afternoon. And you can wind up seeing that, you know, the power, when it goes up and down, you can have gigawatt scale spikes upward and downward on a sort of 15 to 20 minute basis. This is a real challenge that we need to wind up dealing with, and that's what's called ramping is the issue on it. That's one area that we wound up focusing on early, saying how we develop a number of R&D technologies around that for ramping. We also in this past year in the SBIR program looked at a couple of new areas to saying how can we develop smaller scale energy storage that can wind up supporting both EV charging and consumer side of the meter. So having it not on the utility side of the meter, but smaller amounts for residential, commercial, and industrial applications out there. So we've supported to date almost 30 projects in the ARPA-E portfolio around energy storage. Ranges everything from advanced superconductors that can give you very high power density but had very limited duration. So how we can get that to a much longer duration or higher energy, through flywheels, through flow cells, and quite a bit of work in flow cells and advanced electrochemical cells, and then down to things like novel compressed air energy storage technologies. And what we've always focused on this is how we identify that early stage technical challenge, whether it's something like can we improve a membrane for a flow cell, or can we develop a much more robust, highly recyclable or rechargeable cathode or electrode material for a new electrochemical cell. And by solving that technical barrier, we've overcome the challenges that have kept that technology from moving forward in the private sector. We've also looked at where first use makes the greatest impact. And this is over the past year, we've really started focusing more and more on this. So in the lower 48 of the United States, electricity is abundant. It's also, it's fairly cheap. It's on demand. It's available. It's actually a hard place to introduce a new technology. If you look at somewhere like Alaska and Hawaii, electricity can get much, much more expensive. The picture there on the lower left is actually the transmission lines going into Juneau when they got knocked out by an avalanche, right? And so having robust, reliable power is a very challenging situation. In the developing world, electricity is literally, as we heard earlier, the difference between having a standard living and not having a standard living. So having the ability to store and use electricity there is really critical, and also up in Department of Defense applications. So the ability to use fuels more effectively, that's more and more important. So looking at how we can develop technologies first in those more expensive markets that then have long-range impact in the U.S. as well, in the traditional market. So really looking at hierarchy of where are some new emerging needs for energy storage. So you look at things like in household storage or nanogrids for the developing world, moving into microgrids and better primary fuel efficiency, to where you have just a weak emerging grid that you wind up having greater robustness, but it winds up making a much more stable resource. So these are areas where there's kind of first market opportunities in energy storage that will wind up moving more towards the long-term utility scale storage that we see in this country. So with that, that's what we've been thinking about in energy storage over the past year or so. And I invite your comments on this and look forward to some feedback. And with that, I'll leave this up here. I think next up is Tim Heidel.
Great. So thank you for the introduction, Mark. I wanted to spend the next couple minutes talking a little bit more about our investments specifically related to electricity delivery and transmission. Great. So as Mark alluded to, the grid over the next several decades is going to be facing an enormous number of new challenges, from aging infrastructure to changing demand profiles to increasing natural gas generation and the shift away from coal generation, increases in wind and solar generation, and perhaps the decentralization of the entire system. Now, we can't predict exactly what's going to happen. But when we looked at these issues and we looked at these problems and said, well, what can ARPA-E do in this area? We said, well, you know what? There's a common feature to all of these problems, and that's the need for additional flexibility in the actual grid itself. And so we said, what technologies can solve that flexibility problem? And we went out and tried to find some. So if you look at the way we've historically controlled the grid, it's largely been through generation set points. We have very little control directly over how power actually distributes itself within the network itself and where power flows once it's delivered onto that network. But we said, maybe there's other ways of controlling it. Maybe there are other control points we can think about. And so we thought about, well, what might these be? And we said, well, maybe we can control in the grid. Maybe we can put power flow controllers. Both AC power flow controllers or maybe augment the grid with complementary HVDC technology. As Marcus already mentioned, energy storage is a fantastic way of adding flexibility to the grid. And so how do we optimize that electricity storage, assuming that it actually comes? And then finally, the demand side has a real critical piece to play here as well. And more active optimization and control of customer uses is also another way that you can think about actually enabling power flow control throughout the grid. So we launched a program, the Genie program, a little over a year ago now, focusing on power flow control. And about half of the projects in that program are based on hardware advances that promise to dramatically reduce the costs and increase the efficiency of power flow controllers. What you're seeing appear in the upper left is the conventional solution. This is a picture of an actual installation in New York. And what you're looking at are massive series strings of power electronic devices, low voltage devices that they have to string literally hundreds together in order to affect power flow. Turned out that this was an enormously expensive installation. However, the benefits that it returned were actually far larger than the cost itself. Unfortunately, just due to the complexity of it and the number of moving pieces inside of it, we haven't seen many of these devices deployed. And so we said, well, are there ideas out there that can dramatically reduce complexity and dramatically reduce costs so that we can start to achieve ubiquitous deployments? What you're seeing on the right are 4 different approaches. And they use slightly different physical phenomena, and they give you different performance. But we believe, if successful, and we're demonstrating them in the lab now, these all could give you far more control over power flows in AC networks. This program also has several projects related to dramatically reducing the cost of HVDC technology, which could also be an important enabler for power flow control. Of course, at the core of all of these concepts are power electronic components. We also have a program that was started about 2.5 years ago, the ADEPT program, and followed on with a program called Solar ADEPT, focused on solar inverters. That's all about the components. It's projects focused on high voltage power electronic devices. It's focused on low-cost, high-frequency magnetic materials, all that can operate at elevated temperature and could someday be relevant and specifically integrated into these power flow controllers. And so these are a couple images from the successes we've had in the ADEPT program. Now, there's lots more work to do, and there's a lot of scale-up that will have to happen. But this area of finding better components is something that we'll certainly continue to focus on in the years ahead. Now, once you have the hardware devices, you need some way of dispatching and optimizing them. And so if you look out over the last 10 years and you see what have been the advances in other industries related to optimization, there have been just phenomenal advances related to high-performance computing and the emergence of cloud infrastructure, as well as new optimization methods and improvements in solvers. And all of those advances can be applied to better optimizing the grid both today and in the future when we have these new power flow controllers. And so our Genie program, the other half of it is software advances, looking at things like distributed control, looking at the optimization of energy storage resources, or transmission switching, where you start to actually put the availability of each transmission line into the optimization process in and of itself. And so all of these projects are about a year in. You'll be learning about them more in the summit downstairs over the next couple days. I'd love to also talk to you about other ideas related to these. So in the future, what are we going to be doing? Well, there's certainly a lot more work to be done on the components side. Even higher voltage and higher current devices, high voltage and long life, high capacity capacitors. There's a real need for new capacitor technology. I've already talked about AC power flow controllers and multi-terminal HVDC technologies. We'll continue to work on high frequency, low loss magnetics. Not only does it have the potential to transform the electric grid, but those same materials are going to make their way into every electronic device that we use today and make them more efficient and more cost effective. I've talked about new grid control architectures. Eventually, we really need to be starting to think about real-time control architectures for the grid, where we're doing very fast state estimation and stability calculations. Such technologies would literally transform the way that our power grid is operated. So over the next couple of days, I look forward to the dialogue. I'd really love to hear all of your ideas in this area, and I look forward to working together. Thank you.
Thank you, Tim. Next will be Karma Sawyer.
Good afternoon, everyone. It's been 23 years since the Clean Air Act was amended, allowing the EPA to regulate emissions from major stationary sources. And the electricity generation sector has responded to that and become progressively more clean, regulating things like mercury and acid gas emissions. You remember when acid gas was something that was regularly discussed, and that's waned in recent years. We expect that that trend will continue, and the next major hurdle for this space will be dealing with carbon emissions. And that challenge from a technical perspective is far more difficult than anything the sector has faced before in this area because of the chemistry of CO2 and because of the scale of the problem. And we're not ready. ARPA-E has been investing in this space for exactly that reason. Our coal fleet accounts for more than 300 gigawatts of generation. That's 40% of our electricity and accounts for 2 billion tons of CO2 being emitted annually just in the US. And that pales in comparison to the international growth that we're seeing now and expect to continue to see. If you take state-of-the-art technologies for carbon capture and use them to capture CO2 from any of these coal plants, you would increase the cost of electricity by 60 to 80%. ARPA-E's goal has been to cut that in half so that you can enable the continued use of an inexpensive and domestic resource, but without the externalities of CO2 emissions. So ARPA-E has been funding in this space since the very first open funding solicitation in 2009. 5 projects were selected for $13 million. Immediately following that, we announced a focus program area on carbon capture, specifically focused on post-combustion carbon capture for the retrofit space. There were 15 projects selected there for roughly $40 million. And we're continuing to invest here, and this is still an active area of interest for ARPA-E. In our most recent solicitation, more projects were invested in this space. The other thing you'll see on this slide is that we funded across technologies, things that might be considered more typical, things like solvents, although I would argue that none of the solvent projects that we've selected would be classified that way when you look at them in any amount of detail, and including things like phase change and solid materials that can also bind CO2. Now, it's much easier for me to just tell you examples of the types of things we funded to understand how carbon capture at ARPA-E looks different than other investments you might see. So here are 3 examples. The first is a liquid that binds to CO2 and forms a solid. This is a project that's being undertaken at GE. And this might not seem all that interesting to you, but one of the major challenges of carbon capture technologies is the amount of energy used to bind CO2 and then regenerate it thermally. This phase change process allows you to isolate only the molecules that have bound to CO2 via the phase change, so you're not carrying additional material back and forth and heating and cooling it. We've also invested in a team at Texas A&M University that is investing in stable metal organic frameworks. These materials are really ideally suited for the toxic environment of a coal exhaust stream. They've been boiled in water for 7 days and maintain their extremely high capacity for CO2. They've been exposed to high concentrations of acid, and they're still able to maintain their performance. Additionally, we funded a project at Lawrence Livermore National Lab that is rapidly increasing the rate of CO2 sorption. They have biomimetic catalysts that they're putting in a CO2 binding solution inside of these little capsules that you see. Those capsules are about 0.5 millimeter in diameter. So the surface area the CO2 is exposed to is greatly enhanced by the capsules, but the catalysis is inside the capsule as well, giving you one additional boost forward. But even with all the great technical advances that these teams have made over the last 3 years, there's still a lot of challenges ahead in this space, not the least of which are the non-technical ones. While I said that it's generally expected that carbon pricing will come into our lives in the energy community at some point, we have no idea when that will happen and what it will look like. And coal plants are retiring in the U.S. That being said, there will still be a substantial base of them that will last for many years to come. They're being replaced by natural gas-fired power plants. In the future, if there's a need to regulate CO2 emissions from those plants, it will be much more difficult. The concentration of CO2 coming out of that exhaust stream is about 1/3 of that from a coal-fired power plant, making the capture process itself more and more difficult. And like every other project that you hear about in energy, there's a massive challenge of scale up here. Coal-fired power plants are huge. And that's great for generating electricity, but it's terrible when you're trying to deal with the externality of doing that generation. This challenge will require some truly innovative engineering to be able to move from the lab, bench, and small pilot projects that we've funded to something that can actually operate on the scale of power generation. But there's a lot of room for new innovation in this space, and I really encourage all of you to think about this challenging gas separation problem. There are needs for computational screening, a lot of interest in new thermal integration schemes, new membranes, different methods for actually doing the separation itself. Me personally, I'm very interested in non-chemical processes that will not have a large waste stream associated with them. I encourage you to text in your ideas to me. I'm always happy to hear them, and we always want to get new people onto the scene here. Thank you.
Thank you, Karma. Before we move on to our last speaker, I just want to remind people that we're actually getting questions coming in by our Twitter feed or feed them in terms of texting those questions in. We're looking forward to having a robust discussion here at the end, so looking forward to seeing those as they show up. So our fourth speaker here today is Howard Branz, and with that, Howard.
Thank you. I'd like to talk today about the future of solar energy technology. At ARPA-E, we often like to quote the hockey great, Wayne Gretzky, who was asked how he scored so many goals, and he said, "I don't skate to where the puck is. You have to skate to where the puck is going to be." So let's have a quick look at where photovoltaic and concentrating solar power technologies are today under the auspices of the industry and the leadership of the Sunshot program at DOE, and then I'll try to get to the future vision that we're exploring right now. Oh, it's me that has to advance. All right. So the talk is about what happens beyond grid parity, which is where PV is heading. So that graph you're seeing is the PV module price in constant dollars, and it has come down remarkably. I've been in the photovoltaic field for about 30 years, and it's come down an order of magnitude. The amount deployed has gone up by a factor of 10 to the 5, 100,000. Very soon, it's now dipping into grid parity. Grid parity depends on what the utility price is and how sunny it is, so there's no one number that represents grid parity, but we're definitely there. And it's going to come down a lot. And there's going to be so much solar. We're going to have a glut of daytime solar electricity. What are we going to do with it all? Well, the problem is battery technology will unlikely be able to pick up the challenge because you have to have something that discharges and charges once a day, and that's beyond what batteries can probably do. And we're going to have a hard time getting solar into the transportation sector that way. On the other hand, concentrating solar power will probably continue to grow. It stores solar heat. Unlike PV, which is probably going to be in the 20 to 30% range in efficiency, it can take 60% of the full solar spectrum as heat and give you high-value renewable electricity after sunset and when the clouds come out. The problem is it's more expensive today, and it'll probably stay more expensive because of the high complexity. So where do we think we have to go? We have to use more of the solar spectrum. We have to use the solar spectrum better. Solar energy isn't very dense. It doesn't come down, it comes down to about 1 kilowatt per square meter, and that means once you have an aperture area, be it a lens or a mirror, you have to get very high efficiency in converting it into something you can use. So this toolbox we have to work with is the solar to heat efficiency at about 60%, which uses a wide spectrum, as you can see by that bracket. Then solar to electrons, which really gets less and less efficient as you move down even into the mid-infrared and the near-infrared. I mean, into the mid and far-infrared. It's not that effective. And you can have systems where you have a single aperture and optimize the heat to electricity ratio. And I'll try to give you an example in a minute. But the simplest idea is to take and store the heat thermally and get dispatchable solar electricity at the same time as you get daylight electricity. So let me just give you one example. This isn't meant to be prescriptive. I'm sure you all have better ideas, but we've been just exploring a few examples, and this is one of the most interesting. You bring in concentrated sunlight in there, those multicolored rays. You have them hit a PV cell, which, contrary to your intuition, we want to run at very high temperature, between 200 and 400 Celsius. It's going to hurt the efficiency. Maybe you only get 20% out of it. But all the waste heat, the other 80% of waste heat, then goes into a thermal fluid. You see the lower pipe there. We get then 30, 40% of the 80% as an additional 15%. And then why not put a reflector behind the PV and get a third source of energy that is have the subgap infrared light go to a second fluid or perhaps just a higher temperature version of the first one. Now, there's a lot of challenges in this. Optical thermal system design. There's a lot of other versions you can imagine using new optical components, photonics, dichroic mirrors. It doesn't have to look like this, but the basic idea is to get a lot more of the spectrum. And in this particular case, we need to have durable wide gap photovoltaics for 200 to 400 degree C use. And really only NASA's gone into that space for the Mercury mission, and they're looking at it for Venus. But these things can be done at quite high efficiency under concentration. So the second concept is you take that heat and that electricity and you put them together. They come out simultaneously because they're coming out of one aperture when the sun is shining. You put them together to make chemically stored solar energy that you can then put either into the transportation sector or generate electricity. So I'll give you two examples of what we're looking at now. You can do chemical cycles, and the nuclear industry has actually looked into this, where a chemical substrate goes through a thermal cycle, high temperature with the solar heat, and then an electrochemical, and the substrate recycles, and you get some chemical fuel product out. Usually people have aimed at hydrogen, but you can imagine going after carbon monoxide or many other products. And secondly, just high temperature electrolysis. You can take essentially a fuel cell, run it in reverse, or a molten carbonate electrolysis cell and run it. And the advantage you get is that as you raise the temperature, not only do the kinetics get faster, but the thermodynamics start helping you. You can start putting in, so this is the enthalpy that you're putting in the reaction. That's that top horizontal line. And you can see the Gibbs free energy shows how much electricity you have to put in, right? The rest is T delta S, and that can come in as heat. And solar heat is today and probably will remain cheaper than solar electricity. So why not put some electricity and some solar heat into the process, and you can get an electrical storage efficiency that exceeds 100%. No thermodynamics is violated. You're getting the rest of the energy from the heat. A lot of challenges there. Right now, electrolysis usually gets its heat from the overpotential, so you have to reduce the overpotentials. You have to learn to capture solar heat in reactions better. You have to deal with solar intermittency, which is the nightmare of chemical engineers trying to make a plan. So what do we see after grid parity? It has all the hallmarks of the kind of things ARPA is interested in. Technology needs. We need that solar after the daytime is over. Technology opportunities. These interesting systems level problems, and also optics problems, new kinds of solar cells, and chemical storage techniques. Believe it or not, the CSP and PV communities talk together very infrequently. And so we would like to start catalyzing a conversation there, and then the thermoelectrochemistry communities even less. And finally, there would be aggressive technical metrics if we decide to go down the program route there. We want to have your best ideas. We'll likely be running a workshop on this in the near future, so find me sometime or send your ideas. If you think you have something strong to contribute to this space, send a resume, and we'll try to get you an invitation to the workshop. So thank you very much.
You can stay here to ask questions. Great. Well, with that, we hope to move forward to is answering a few questions that people have started feeding into the feed here. I'm going to take off first and ask each of my panelists here, if you had one thing that you wish in your area someone could invent, what's that one thing that you wish they would invent? I'm going to pick the person who looks the least quizzical on this to begin with.
Yeah,
so, Howard.
I'll go with an ideal spectrum splitter, low loss that can operate on, say, 500x concentrated sunlight, and send it to 3 different physical locations, say. Even 3 would make me happy. IR over here. I want to go beyond the cold mirrors and hot mirrors we have today. IR over here, high-end visible over here, and low-end visible and near IR at some other location. And maybe 4 would be nice too, but lossless. It has to be really low loss.
Great. Karma?
Oh man, this is tough. I think I'm going to go to thermal integration schemes, and this is a really broad category, but in general I feel like there's a lot of opportunity missed in chemical cycles to be able to harness heat that is actually released or needed at various parts of chemical reactions through various entropic losses, for example, and so some new engineering schemes around that, which I know is an old space. I'd love to be able to see more there.
So I think if you think about the way the grid's operated today, there's an enormous number of assumptions that go into just even calculating power flows. And I think that if you could actually invent a very fast way of assessing the state of the grid and the stability of the grid in real time, I mean, everything would change if you could get that. And so it's real fundamental math. The ways that we calculate the power flows today probably aren't going to work for us.
And of course, I have to ask the question of myself. So in energy storage, what we're seeing a lot are a lot of new, very, very high current density technologies around flow batteries and new electrochemical cells, where the cost of energy you have is basically driven by a couple of things. One is what's the raw materials that you're using for your anode and your cathode, assuming an electrochemical approach. And so that's set between somewhere, let's say, 1 to 4 volts, based on just the thermodynamics that you have as a range across there. You're really driving for the lowest dollar per EMF that you can have there. And once that's fixed, getting as much current density through that reversibly as possible. So really new ways of thinking about getting very, very high current density with low side reactions on it and not having unintended reactions. That's a very broad statement. What we're seeing is actually some real interesting breakthroughs in catalysts and membrane technology. And what this brings out is that the heart of the technology is in that middle layer. It's not just developing the new storage battery, for lack of a term. It's developing better, MEAs, membrane electrode assemblies, new catalyst formulations, things like that. Are really some great white space looking at how we can get beyond things like platinum catalysts that are very low cost materials. So I think in that area is some science area that we'd be looking at. So my reason for asking that question of all our panelists up here is we're really looking for questions here. I'm going to let Tim ask the first question that we have up here at this point then, because it's actually directed at me.
Okay. So Mark, given what you've experienced with the GRIDS program and what you've seen over the last several years, what are you considering, or what would you consider the most promising energy storage technologies today?
Yeah. So I've been, as I've mentioned, been around ARPA-E almost 3 years here, and it's been a very, very exciting time, and actually a really, really rewarding thing to watch is how the community has responded to this challenge of really low-cost energy storage technologies. And first and foremost, you can look at this and say, wow, I thought ARPA-E was a technology agency. Why are you putting a cost metric up there? And the reason is, and someone recently shared this with me, was that when we first put that solicitation out, they thought that we were nuts. They said, this is impossible. How can anyone do this? And they were right. For the existing technologies that existed at that point, it would have been very, very challenging to ever get to those cost points. So what it forced the community to do is think new about that problem. So if you look at getting back to this current density question, state of the art at that time for things like a flow battery or most electrochemical cells was on the order of 50 to 200 milliamps per square centimeter with fairly high round trip efficiency. What's really interesting to watch that I've gotten really excited about is First United Technologies showed this in the flow battery, and then we've got it in some other technologies out there where you could go to 800 milliamps, 1200 milliamps, really a step function, almost an order of magnitude step function in the current density you could achieve while maintaining high round trip efficiency. Now what's interesting is this is not a standstill. The other thing we've seen is looking in the scientific literature. The U.S. started publishing that. A number of our researchers and also people that are in the scientific community that said, hey, this is a new way to think about it. ARPA-E is looking in this area. Let's see what we can do with some of our new ideas out there. And seeing that response that wound up happening, but what's happening now is you've got around the world other researchers that are starting to step up as well. So we can't stay static at that. So to give you a long answer to that short question, what I'm really excited about are some very, very high current density flow batteries, looking at where we can use low-cost electrolytes to wind up getting that high energy efficiency and cost point.
Great. So I think I'll read the next question before handing it back to Mark, since I've actually been able to read it. And the question is directed towards Howard. Howard, have you considered the role for new phosphor materials, materials capable of doing photon wavelength conversion to support the hybrid solar concepts you're thinking of?
The question was about new phosphor materials. You know, it'll have to be very high conversion efficiency. You know, I'd rather use the reason phosphors aren't the first thing that comes to mind is that normally you're taking a high energy photon and converting it to a low energy photon. So you've already lost some energy as heat in that phosphor. And what you'd rather do is go the other way and split off the UV and use it for photolysis into a chemical storage reaction. Or something like that. I mean, photovoltaics at a given wave, at a given band edge, a given band gap is quite efficient, except when the photons are far too energetic, and then you have thermalization losses down to the band edge. Well, if you take the phosphors, you take the high energy photons and put them down at the band edge, that mimics the same problems that remain for photovoltaics. You know, if someone can show me a way to do that where you split the photon into two, we'd love to see that.
Great, thanks. Well, Tim, this question's for you then. So have you thought a little bit about the role and some technology issues around self-healing grids? In particular, are there cross-cutting technologies that might be leveraged across the IT sectors and data storage that can be solved in this? To highlight that, you look at the recent storms and outages in the U.S., and that really highlighted the importance of reliability. So what are some of the technology issues that you could look at in that area?
Yeah, so I mean, every day, right? So automation technologies in general will allow you to achieve some of that self-healing capabilities. We've got several projects in our current portfolio that are actually focused on post-contingency actions. You've had something happen. You've had a line go down or a generator trip offline, and they're actually doing calculations in real time based on real data to be able to recover and adapt to that. It's something that historically we've always based all of those decisions on offline simulations and or operator intuition. And I think making that more automated is something that will be happening in the future. If you look at different technology areas where there's perhaps some inspiration, the cloud computing infrastructure community is one that I've been looking at quite a bit lately. And it's not one that I knew anything about before coming to ARPA-E. It's a community that has really found technological solutions to dealing with systems and networks in which you don't really ever know what your state is. There's a lot of replication of data, and how do you hand off from one server to another in order to continue doing things in a time-critical fashion with very, very high reliability. You know, I'm not saying all those technologies will translate directly to the grid, but there's a lot of interesting innovation that's happening there that is absolutely relevant.
I think the interesting thing you pointed up, that it's the whole issue of making that reliability and being able to understand what do you do with contingency afterwards. I think the highlight this past month was, you know, in the Super Bowl, right? You had a blackout. From what I understand, it was a matter of minutes before they figured out what the problem was, but it was all that checking to make sure it's safe to respond afterwards and re-energize the circuits that take a period of time afterwards. And so that's certainly a key issue. As a follow-up on that, on the other side, in adopting technologies, what do you think about the role of sort of deregulated markets and things like PJM incentivizing getting technologies out to the marketplace? And how do we think about that around ARPA-E and some of the teams that you've been working with?
Yeah. So right from day one with all of our teams, we would tell them, go out and figure out how you're going to sell this. What's the first market? And sometimes that first market exists because of the incentives that exist in competitive wholesale markets. Right. Other times that first market is a pilot program. PJM, for example, has a great pilot program where they're actually allowing a whole bunch of different companies to test out technologies right from day one, early stage. But ultimately, you're solving a utility problem. Right. You're getting paid by half a dozen different ways, but you're solving a utility problem. And I think the most successful companies I've seen in our portfolio are the ones who have said, what is the utility problem that we're solving? Let's go talk to the utility. And if you can get it cheap enough and if you can get it reliable enough, that utility is actually going to deploy that technology. A favorite example of mine, and I think the SmartWire Grid folks are here today, technology program within the Genie program. And they have a technology that is very low cost, really robust, and they've been able to actually go out and talk to utilities and say, we're going to solve a problem you have today. and they actually installed 99 devices in a pilot last October. So it's something we're really excited about. Those market opportunities do exist.
Yep. Yeah. I mean, I think that's a good example. If you look at the energy storage problem, it's an area where every utility, they have somebody that's looking at energy storage right now. It's sort of viewed as a holy grail of the future. No one's quite figured out how to do that, right? And what's the utility problem it exactly solves? What's the regulatory framework? With some limited, notable, very, very important exceptions to that. But that's the challenge of getting these technologies forward. And I think the extreme case, Karma, is for you is, and you might want to comment on it, is you're developing a technology where there really is a lot of regulatory uncertainty. But that's ARPA-E's job, isn't it? We're supposed to be developing technologies where there's too much risk for the private sector or other parts of the government to invest in anyway, right?
I completely agree. If there wasn't people like ARPA-E or people like fossil energy whose mission it was to deal with the carbon problem, it's completely uncertain when that carbon price will come and at what rate we will have to ramp up. And there's a massive technical gap, and you need people to be able to absorb that risk and handle it up front. There are other first markets that are coming on board in carbon capture as well, enhanced oil recovery or conversions of CO2 to other sorts of chemicals or fuels. But those are going to be niche markets because of the scale of CO2 capture. Ultimately, to actually be able to deal with the CO2 emissions from coal plants, you have to be able to move beyond that. And we're just not at a point in a regulation space to do that yet.
Great. Well, with that, I've gotten a notice that we're trying to get back on track today. I'm sorry we've been running a little late. I think the next session is the government networking session after this, and I thank you all. Please come up and ask us questions. We're here to engage with you all week, and so we're looking forward to that dialogue. So thank you very much.